This is lecture 15 in BBSP 610. We're going to be discussing confidence intervals and hypothesis tests for proportions. So first, let's briefly discuss the difference between means and proportions. That say we take a sample of 100 people and record how tall each person is and take their average height. That would be a mean that we're going to perform hypothesis testing on or calculating confidence intervals or whatever. But we might also interview 100 people and ask them whether or not they approve of the job Obama is doing as president. In that case, we would be measuring a proportion rather than a mean. Other examples of one sample proportion. Say we flip a coin 1,000 times and we want to calculate the proportion of heads. Say we want to know whether or not the coin's weighted, or the example I just gave, calculating the president's approval rating, and say we want to estimate what proportion of the offspring of a Drosophila with the novel mutation also have the mutation. We might want to answer the question of whether the mutation is dominant or recessive, or whether it has some other pattern of inheritance. So sample proportions are computed as follows. It's defined to be p hat, which is equal to x divided by n, where n is the number of trials and x is the number of successes. For example, if we do a telephone interview to calculate Obama's approval rating, n would be the number of people that we called, and x would be the number of people who approved of the job that Obama's doing. We denote the true probability of success, the president's true approval rating or whatever, as p, which is a parameter. And if we draw a random sample of size n from a large population with true probability of success p, then for sufficiently large n, the sample proportion should be approximately normally distributed with mean p and standard deviation square root of p times 1 minus p divided by n. And in order for these conditions, in order for this approximation to be valid, you have to have n must be sufficiently large and p must not be too small. That the usual rule of thumb is the normal approximation is okay if n times p is greater than 10 and n times 1 minus p is also greater than 10. So the population should be at least as 10 times, and also the population should be at least 10 times as large as the sample size, which in practice is almost always the case. In these conditions, or if anything a bit conservative, you'll usually get away with it even if these aren't satisfied, but you're generally safe if those conditions are satisfied. So if the conditions on the previous slide are satisfied, then we can compute confidence intervals for the sample proportion, just using the properties of the normal distribution that we take p hat plus or minus the appropriate quantile of the standard normal distribution z star times the estimate of the standard error of the proportion, which would be p hat times 1 minus p hat divided by n. Z star would be 1.96 for a 95% confidence interval. Similarly, if you want to do hypothesis testing for proportions, to test the null hypothesis that p equals p0 against the alternative that is not equal to p0, you can compute a test statistic similar to what we did in the case for means. You take p hat minus p0 divided by the standard error, that is square root p0, 1 minus p0 over n. And under the null hypothesis, z should have a normal distribution with mean 0 and standard deviation 1. So a famous example from the history of biology would be Mendel's peas. As I'm sure you all know, Gregor Mendel discovered the principles of modern human genetics. And one of the ways he did this, he identified a gene that caused peas to become wrinkled. And under Mendel's models of inheritance, he hypothesized that 25% of the offspring of two specific plants should have wrinkled peas. He observed 5,474 smooth peas and 1850 wrinkled peas. So are his data consistent with this hypothesis? Well, One way you can do this is by using the formulas that I described on the previous slide and calculating them directly in R. We have a total of about, what would it be, about 7,200 P's. Take the number that are wrinkled, divide by the total, then we can compute the p-value for testing the null hypothesis that p is equal to 0.25 by calculating the z-statistic, taking 1 minus that, multiplying by 2 to get the two-sided test, and we can also get confidence intervals using the formula from the previous slide. Take the observed proportion plus or minus the appropriate quantile of the normal times the standard error, which would be p times 1 minus p divided by n. That's kind of a pain. In practice, you don't want to do that. So there's another R command that's simpler called prop.test, where you feed it the proportion of successes, the total number of trials, and the hypothesized value of the proportion. And in this case, we get a p-value of about 0.62 and a confidence interval similar to what we saw in this previous slide. It's not identical for reasons that I'll discuss here in a second. So in general, prop.test, if you say x, comma n, comma p equals p0, it'll test the null hypothesis, the true proportion of success p equals p0, against the alternative that p is not equal to p0 when we observe x successes and n trials. And prop.test accepts parameters alternative, comp.level, most of the same parameters that you can give to t.test, you can also pass to prop.test. And as I mentioned earlier, the p-value and the confidence intervals that we obtained using prop.test are slightly different than what we obtained using our original method. The differences, if you compare the two slides, are pretty trivial, but they're not 100% identical. The reason for this is R doesn't use the normal approximation for proportions the way I described in the previous slide. It uses a chi-square statistic, which you'll see in the next lecture. For fairly large sample sizes, the two results should be basically identical. The chi-square approach used by R can work better when the proportion of successes is very large or very small, but for practical purposes, you can just treat them as identical. For most cases, they will be. I'll note in passing that it's possible to do exact tests for proportions. Both the normal theory approximation and the chi-square approximation rely on the central limit theorem and hence require large sample sizes. But using modern computers, it's actually possible to compute these p-values and confidence intervals exactly. In R, we don't necessarily need to use these approximations. So for example, say that we flipped a weighted coin 7,324 times where the probability of heads is 0.25. We would expect to observe 1,831 heads. So we may want to calculate the probability of observing 1,850 heads if the true probability is 0.25, or more precisely, what's the probability that the number of heads we observe will be more than 19 away from 1831. In the past, nobody would perform tests like this because calculating this probability without a computer would be a nightmare. But with a computer, it's quite easy. The command in R is called binom.test. The syntax is exactly the same as prop.test. You can see in this case we get p-values and a confidence interval that are virtually identical to what we got using both the normal theory and the chi-square methods. Comparing these methods for large samples, the tests will give nearly identical results. The exact test is more likely to give correct results if your sample size is small. The downside is the confidence intervals may be a little conservative, although, again, that's only an issue for small samples. For larger samples, you won't be able to tell the difference. So you may wonder, why do we still use the normal approximations if we can compute exact tests right now and we never have to worry about the assumptions being violated? And I mean, the short answer is that's basically inertia. That journals, people almost never use this test, it almost never appears in journals, so people don't use it. But in my opinion, it should be used more than it is, but that's the nature of life. So we may also want to compare two different proportions that we may want to test the null hypothesis that is a proportion in one population equal to the proportion in another population. This is similar to what we would do for a two-sample t-test, that rather than saying what's Obama's approval rating, we may want to say, does Obama have a higher approval rating than Boehner? I don't know, just naming some other politician off the top of my head. And this is analogous to the two-sample t-test. We want to test the null hypothesis that two proportions are equal. So some example of two-sample proportions, say we may want to answer the question, is the proportion of children who contract polio after being vaccinated the same as the proportion of children who contract polio after receiving a placebo? Or is the proportion of lung cancer patients who smoke equal to the proportion of smokers in the overall population? That would be a way of testing the null hypothesis that smoking doesn't cause lung cancer. So the notation for this, say we have two samples of size n1 and n2, we observe x1 and x2 successes. The true proportions are denoted by p1 and p2, and the sample proportions would be x1 divided by n1 and x2 divided by n2, just as we would expect. So to compare two proportions, we typically estimate the difference between the two proportions, the first proportion minus the second proportion. This is known as the risk difference in epidemiology. I'll discuss what it means in a little more detail in a few slides down. But using a normal theory approximation, we can show that the distribution of this difference should be approximately normally distributed, with mean p1 minus p2 and standard deviation square root of p1 1 minus p1 over n1 plus p2 1 minus p2 over n2. And once again, we need n1 times p1, n1 times 1 minus p1 greater than 10, and likewise for n2 and p2, or the approximation may be invalid. And we can compute confidence intervals for these proportions in the same way as we did in the one sample case. Take the sample difference between the two proportions plus or minus z star times the standard error. Said, don't worry too much about these formulas. I'm never going to ask you to compute this exactly, and R will do it for us, but here's the formulas in case you ever need them. And to test the whole null hypothesis that d equals 0 against the alternative that d is non-zero, you can use the test statistic on this slide. You'll notice that it's a little different than what you saw on the previous slide. The reason for this is because under the null hypothesis, the two proportions are equal, so p1 equals p2, so you can just factor p hat times 1 minus p hat out of the denominator, where p hat is the pooled proportion. Take the count of successes added together by the total number of trials, and that should be normally distributed under the null hypothesis. Again, R will do this for us. Don't worry too much about the details. So, for example, say we're doing a clinical trial for a new pain medication, and we want to see if the new drug provides better pain relief than a placebo. Say, in the treatment group, there are 75 patients with pain relief out of 125, and there's 52 out of 122 in the placebo group. That should say patients with pain relief. This is one more thing that got messed up when I converted this into Keynote. Anyway, We could compute this using p-norm and q-norm using the formulas in the previous slide and the previous couple slides. As you can see, this is an ugly mess. Definitely not something that you would ever want to do in real life, but if you ever wanted to do this for some strange reason, there's the R code that you would use to do it. In practice, I recommend that you use prop.test, which is the first. It takes two vectors, x and y. The first is the counts of successes, the second is the total number of trials. So in this case, the p-value for testing the null hypothesis is about 0.01. At the 0.05 level, we would reject the null hypothesis of no difference between the two groups and conclude that the treatment group is better. And the 95% confidence interval for the difference in the proportions would be from about 4.3% to 30.5%. In general, if you say prop.test and give it two values x1, x2, and n1, n2, test the null hypothesis, the two proportions are equal. When you have x1 successes out of n1 trials and x2 successes out of n2 trials in the second group. And once again, you can add the parameters alternative or conf.level if you want. You can even specify the parameter p equals p0, the difference between the two groups, under the null hypothesis. In practice, though, you almost always want that to be equal to 0. As before, the p-values and confidence intervals calculated by R differ slightly from what we calculated earlier. Again, it uses a chi-square test rather than a normal test. In most cases, it will make very little difference, but just in case you're wondering why the small discrepancies are there. And just little epidemiology note in case you ever see this terminology. Note that there's a difference between the risk difference, which is defined to be the difference in the proportions, and the relative risk, which is the quotient of the proportions. That in this clinical trial example, the risk difference was 0.174, which means that people in the treatment group had a 17.4% greater chance of experiencing pain relief, and the relative risk is 1.41, meaning that patients in the treatment group were 1.41 times more likely to experience pain relief. Why does this difference matter? Well, here's an illustration of the risk difference versus the relative risk. This table shows the death rate per 100,000 from lung cancer and heart disease for both smokers and non-smokers. That among smokers, there were about 140 people per 100,000 who got lung cancer versus 10 among non-smokers. Among smokers, 669 per 100,000 got heart disease versus 413 non-smokers. So the relative risk would be 14 for lung cancer and 1.6 for heart disease, and the risk difference times 100,000 would be 130 versus 256. So what does this mean? The relative risking of smoking is much greater for lung cancer than heart disease, indicating that smoking is much more strongly associated with lung cancer than it is with heart disease. But the risk difference for heart disease is greater, which indicates that if you manage to reduce smoking, you'll actually save more lives from heart disease than you will lives from smoking, even though smoking increases your risk of lung cancer more than it increases your risk of heart disease is simply much more common in the first place, so you would save more lives by reducing heart disease than by reducing lung cancer. And I'm a broken record, but just some general reminders / comments about hypothesis testing is that for a hypothesis test to be valid, you have to have a sample that's representative of the population. Each observation of the sample must be independent of the other samples, and that you should report confidence intervals as well as p-values. And sample size the sample size has to be sufficiently large if for these approximations to be valid, except in the exact test for one sample proportions that I discussed earlier. R will give you a warning if your sample size is too small. Thankfully, R is smart enough to do that. Things to remember from today's lecture is that we can test hypotheses about proportions and finding confidence intervals using an approach similar to what we did for numeric data. All the warnings about t-tests apply to these tests as well, in terms of you have to have a representative sample and they have to be independent and so forth. And if your sample size is too small, you can sometimes get around the problem by using an exact test. Oh, our commands to remember for today: prop.test x, n, p equals p0 will test the null hypothesis that your observed proportion is equal to p0. Binom.test has the same syntax, only it will do an exact test. If you go prop.test x1, x2, n1, n2, that'll test the null hypothesis that two proportions are equal to one another.